Hello everyone, thank you for listening to my talk today. My name is Podschwit and the title of this talk is Fire Danger Classification Models, a Peru Case Study. Today we will discuss how, with the help of my colleagues from the United States Forest Service and the National Meteorology and Hydrology Service of Peru, have modified an existing model of fire danger to better communicate regional conditions. Now, before we begin discussing the specific methods and results used in our analysis, it will be helpful to say a few things about why and how fire danger is measured. The reason why we are interested in future fire danger is that, if known, it allows multiple decision makers to make better decisions that can prevent loss of life, property, economic, and other values. For instance, if we knew that a particular location was at risk of high fire danger in the future, we wouldn't necessarily pre-position firefighters in that location, and we would have public safety officials perhaps help evacuate the general public out of that location. How future fire danger is measured, whether understood or not, is typically with the use of models. That is, information that is deemed relevant to fire danger is synthesized into a single category communicating the level of risk. In the United States, preparedness levels can be interpreted as an example of fire danger models. Here, current and forecasted wildfire activity, current and forecasted meteorology, and resource scarcity is synthesized into a single number between 1 and 5 that is intended to communicate the level of resource demand. Of course, wildfire is a global phenomenon, and it is not only the United States that could benefit from fire danger models. In Peru, wildfire is a phenomenon that occurs throughout the country in diverse landscapes and can result in loss of property, life, environmental, and cultural resources. To manage these risks, fire danger is currently forecasted by tsunami using the fire weather index as a proxy. Under this model, if the fire weather index is less than 6, then fire danger is interpreted as low. If it's between 6 and 12, fire danger is interpreted as moderate. If it's between 12 and 18, it is interpreted as high. If it's between 18 and 24, it's interpreted as very high. And if it's greater than 24, it's interpreted as extreme. However, there are at least two major challenges that arise when using this model in practice that can be roughly thought of as a problem with calibration and a problem with interpretation. The problem with calibration can be seen when this original fire danger model is compared with percentile-based thresholds in various locations within Peru. On the right, you will see a percentile-based threshold shown in the rectangles and the original classification method shown on points. And this is at the Bosque Seco location, which is a coastal, dry region. And what we see is that the original classification model is crying wolf, that in conditions that are quite commonplace, the model is saying that the conditions are extreme. In some locations of the Amazon, we can have the opposite problem. Here, the original model is saying that conditions are low or moderate in conditions that are quite extreme in terms of the 2003 to 2020 climatology. The original fire danger model also suffers from a problem of interpretation. The original model classifies fire danger based on drought activity, not explicitly wildfire activity. This is important, one, because other variables may be important to categorizing fire danger. These could be vegetation characteristics such as fuel levels. Past fire activity are also related to fuel levels, which would be related again to fire danger. Humans can ignite wildfires, and they can also put out fires, and that will be related to fire activity. Ocean temperature has been shown to be related to wildfire activity in some contexts, and it may be important here too. Wind is related to wildfire growth, which would also be related to fire danger. Secondly, the effect of drought on fire activity is not consistent across regions. In the desert southwest, for instance, if we had quite a bit of rain, that may actually exacerbate wildfire conditions because it will increase typically low fuel levels. Whereas if we are somewhere like the northwest where fuel is already high, more rain would typically mean less wildfire because fuel is already abundant, and that just means a wetting of the fuels. So we've identified two major problems with the original model. An issue of calibration, where the models are not tuned to local conditions, and an issue of interpretation, where the model predictions are not explicitly tied to wildfire activity. Now, the way in which we're going to deal with each of these problems is calibration will be dealt with by simply fitting the models at a regional level. The problem of interpretation will be dealt with by defining fire danger categories that are explicitly tied to wildfire activity instead of simply the fire weather index. And we will also allow these models to include other covariates that we think are relevant. Under the modified fire danger model, fire danger will be explicitly tied to wildfire activity by taking the number of hotspot detects in the next week and transforming it into a categorical variable. This transformation will happen by using percentile-based thresholds using the 2003 to 2020 data, and these thresholds will conform to a binomial distribution using the parameters that are described on the right. Another change that will happen is the original extreme category used in the original tsunami model is removed. The reason for this is that we had concerns about the number of observations that would fall in this category and the feasibility of fitting a model using such few observations. The model itself will follow a generalized linear model framework using a logit link and assuming a binomial distribution. We will select the best model from a set of 128 candidates, and this set is produced by choosing up to one variable from each of the 4 categories shown on the right. So we're allowed to either take fire weather index or nothing at all, use the previous week's number of hotspot detects or nothing at all. You can use one or none of the oscillation index described there on the right, and you could use the month of the year as a covariate or nothing at all. So we acknowledge that defining a best model is a fraught question, but we have decided to define best as the model that has the highest accuracy. And accuracy was estimated using a stratified cross-validation approach. Specifically, we would iteratively go through and remove 2 years from the 2003 to the 2020 dataset to create a testing dataset. We would fit a model using the remaining 15 years of data, and then using the testing dataset, we would record the percent of days where the model correctly predicted the fire danger category. We repeated this process for all 816 ways of choosing 2 years, and we averaged across all of these iterations and chose the model that had the highest estimated accuracy. And this process is described on the right. Or an example of this process is shown on the right. So this table describes what were the best models for each of the 6 regions of our study. We found in the Bosque Seco that the fire weather index had a positive relationship with wildfire activity, as did the Atlantic multidecadal oscillation, and we found that the month of the year was a useful covariate. In both of the Amazon regions, we found that the fire weather index was not a useful predictor of wildfire activity, but the Atlantic multidecadal oscillation was, as was the month of the year. In the transition region, we found that the fire weather index had a positive relationship with wildfire activity, as did the previous week's hotspot counts. And we found that the oceanic Nino index and the month of the year was also useful. In the Sierra region, we found that the fire weather index and the oceanic Nino index was useful, along with the month of the year. And finally, in the Eredo region, we found that only the month of the year was useful in predicting the future wildfire activity. In terms of the accuracy of the models, we found that they were reasonably good. The highest accuracy was observed in the Bosque Seco region, which had a 74% accuracy, meaning that 74% of the days the model correctly told you what fire danger category it was going to fall into. The lowest accuracy was found in the Eredo region with a 58% accuracy, but even this lowest accuracy was still more accurate than random classification, suggesting that these models could still potentially be useful for actionable information for fire-related decision makers in Peru. Now, what do these forecasts actually look like? Well, there are 2 different products that can be produced from this model. The first is something that would be typically expected for most people, which is a map of expected fire danger conditions for the next 7 days. And again, these models are dealing with the 2 problems that we identified earlier. The issue of calibration is dealt with because they are relativized to regional conditions, and they are explicitly tied to wildfire activity, dealing with our problem of interpretation. But at any rate, we were able to produce maps of Peru that would tell you regionally where wildfire in the subsequent week was expected to be high. The models produced in this framework could also be used to produce probabilistic forecasts. For instance, we could do something like zoom up on the Bosque Seco region for the day of January 1st, 2010, and assign probabilities that in the next 7 days we will be in one of the fire danger categories. we could say something like there's an 80% chance that the future fire conditions will be low, but also a 20% chance that they're moderate and a negligible chance that they're high or very high. This has the advantage of communicating the uncertainty in the predictions, which would be particularly useful for fire-related decisions that are particularly costly. Although we believe that the models we produced were quite successful at what they set out to do, there are still a number of tasks that remain to be done. Most important of which is to continue the validation of these models using 2021 data. The holdout method is considered by many to be the gold standard of assessing model performance, and validating these models using the 2021 data, the out-of-sample data, we think is incredibly important for establishing the credibility of these models. We also want to try to modify these models so they can be used at non-weekly forecast horizons. We want to be able to provide predictions about fire danger tomorrow or fire danger a month from today. We also want to try to improve the performance of these models by including other covariates. We found that substituting fire weather index for other dryness indices like the energy release component or the burning index or KVDI didn't do much in terms of improving the accuracy of these models. So for that reason, we believe that including things like NDVI, things that are uncorrelated with the dryness, may improve the performance better than just sort of substituting different covariates that would fall into the categories that we described earlier. Before we also make these models public, we want to collaborate with fire-related decision makers, particularly those in Peru, to verify that the information that we produce is communicated clearly and is actually going to be useful for decisions that they'll be making in the future. I would like to thank our collaborators, Matt Jolly at the United States Forest Service, Ernesto Alvarado at the United States Forest Service and the University of Washington, Blanca Vigo at the United States Forest Service, Andrea Marcos at the United States Forest Service, Vanya Aliga at Tsunami, and Diego Zimmerman at Tsunami. I would also like to thank our South American collaborators in Colombia. I'd also like to thank the Fire Ecology and Management Laboratory at the University of Washington for helping me with earlier versions of this talk. And I'd also like to thank our institutional supporters at ORISE, the United States Forest Service, and Tsunami. And with that, I would like to close, and here are the photo credits used in my talk. Thank you very much.